Greetings and salutations, magical chemists. I hope you're hungry, because we're going to talk about rice. Rice tables, that is. Many equilibrium calculations are solved using rice tables, which are an organizational method used to track what happens as a reaction approaches equilibrium. The R in rice stands for balanced reaction, and I stands for the initial concentrations or pressures of each species in the reaction mixture. Please be careful. Unlike the rice tables we used in stoichiometry, we cannot use moles in our rice table. It has to be concentration or pressure. The C stands for change in concentration or pressure for each species as the system moves towards equilibrium. It is important to note that everything changes stoichiometrically. This is why it's so important to have a balanced equation. And then E, of course, stands for equilibrium. What is the equilibrium concentration or pressure? One more note, because it's so important. I'm going to say it again. If the amounts are given in moles, watch out. You've got to convert to molarity. Let's go ahead and take a look at an example so you can see what a rice table looks like in terms of equilibrium. So in this example, we've given a specific reaction, the decomposition of sulfur trioxide into oxygen and sulfur dioxide. And it also tells you the initial concentration of sulfur trioxide, and it tells you at equilibrium the concentration of SO2. And we're supposed to take this information and use it to calculate the value of the equilibrium constant, K. So I've already created a rice table, so we can just fill in the values. Well, we're starting with, conveniently they gave us everything in concentration, so that makes our lives easy. We just need to fill in the initial concentrations. Well, they told us the initial SO3 concentration was 0.020 molar. Remember, we don't actually write the units in the rice table, just the numerical value, which is why it's so essential to remember that's molarity. Okay, you might be thinking, well, wait, they didn't tell me anything about oxygen or SO2. Well, if they didn't tell you anything about their initial concentration, we assume that they are 0. Next, we have the change row. The change row is determined by stoichiometry. That means we need to look at the coefficient on the balanced equation. First, it's important to recognize that since all you have are reactants, some of them are going to turn into products. So the change of your reactants is going to be negative. Now, we don't actually know yet how much of the reactants are getting used up. So we're going to put this in terms of X. But because SO3 has a stoichiometric coefficient of 2, we're going to say that this is going to lose 2X. Now, the product side, neither one of those chemicals have any concentration at all, so they're going to be gaining. How much are they gaining? Well, it's in terms of X. O2 has a stoichiometric coefficient of 1, so it's gaining just X. But SO2 has a stoichiometric coefficient of 2, so it's gaining 2X. So to find the equilibrium concentration, all you need to do is take your initial concentration and add or subtract the change. That's it. So the equilibrium concentration of SO3 is going to be 0.020 minus 2X. The equilibrium concentration of O2 is just going to be X. And the equilibrium concentration of SO2 is going to be 2X. You might be thinking, but wait, what good does that do me? I don't have any numbers. Well, actually, you do. There was one more piece of information given in the problem. They said at equilibrium, the concentration of SO2 is 0.012 molar. Well, I also know the concentration of SO2 at equilibrium is 2X. So 2X equals 0.012, which of course means now we can solve for X. Because we can solve for X, now we can go back and find the equilibrium concentrations of the other species present in this reaction. Of course, the concentration of oxygen at equilibrium was X, so that's easy. And then for SO3, we just need to plug into our expression. Notice when we solve for SO3, because of the rules of sig figs and place values when we're subtracting, we have to round to 3 numbers after the decimal point, which means we only get 1 sig fig for the concentration of SO3 at equilibrium. But sig figs or not, now I have numerical values for SO3, O2, and SO2 for equilibrium concentrations. So now I want to calculate K. Perfect, I just plug these into my equilibrium constant expression. K, of course, is the ratio of products to reactants, so now I just need to plug in the values that I have. When I plug my values in numerically, I get 0.0135, but I only get to keep 1 sig fig. Yay! So for this reaction, at this temperature, the value of the equilibrium constant is 0.01. And we're done. Okay, so we are given a different reaction, and it says reaction mixture at 1700 degrees Celsius, warm, contains methane in 0.115 molar concentration. And then at equilibrium, the mixture is going to contain 0.035 molar of C2H2. So we want to find the equilibrium constant. So once again, our very first step is to set up a delicious rice table. The best way to do that is to start by writing the reaction, but make sure to give yourself a little bit of space. Don't write it too close together. Once you've done that, you can label your rice table. So just R-I-C-E and delicious. Eventually, you don't actually have to label it as rice. You just have to go and follow through the steps, but it's a nice way to keep track, especially at the beginning. So let's go ahead and fill in the information we know. Initially, they told us how much CH4 we had. It was 0.115 molar. And then, at equilibrium, they gave us the concentration of C2H2. Okay, and then I realized it could be nice to have some dividing lines to help keep track of everything. So that's all the information they gave us, but that's enough. So remember, since they didn't talk at all about the products, that meant there were no products at the beginning, so we can fill in each of these as having an initial concentration of 0. And now we get to use the joys of stoichiometry to fill in the change column. Now this is where using those stoichiometric coefficients really comes in handy, because the coefficients aren't just 1 anymore. Since the coefficient of CH4 is 2, that means the amount lost isn't just going to be x anymore. This time it's going to be 2x. Now our products, of course, are going to be positive because they're gaining. The stoichiometric coefficient of C2H2 is 1, so this is just you're adding x. But the coefficient of hydrogen gas is 3. So as the reaction runs, every time it changes, you're producing 3 times the amount of x. So now we have enough information to fill in the rest of our chart. All we need to do is add together the things in the first 2 rows to get the information for what's happening at equilibrium. So for CH4 at equilibrium, you're going to have its initial concentration, 0.115, minus 2x. And then for hydrogen gas, well, you just have 3x because it didn't start off with anything at all. You may have noticed in this case that we totally know the value of x because the amount of C2H2 produced, because the stoichiometric coefficient was 1, is simply x. That means our x value is 0.035. So now that we know that, we can go back and solve for the concentration of CH4 and H2. I realized in the previous problem I forgot to label these as equilibrium concentrations we're solving for, but they are. So that's why you label the concentration with a little subscript of EQ. And then all we need to do is plug into the equilibrium expression that we derived in our rice table. So when we plug in our value for x into the CH4 expression, we get that the remaining concentration at equilibrium is 0.054 molar. Now we can do the same thing to find the equilibrium concentration of hydrogen gas. This time, of course, we're plugging x into the 3x expression. And so when you do that, you get 0.105 molar. Now, remember, you only get to keep 2 sig figs from this number, but we don't want to round until we get to the end of the problem. Now we have everything we need to plug back into the equilibrium constant expression and solve for the value of the equilibrium constant. First, of course, you actually need to write out your equilibrium constant expression and then plug in the values. And since we only get to keep 2 sig figs, that gives us our final equilibrium constant value of 0.020. Ta-da! So that is how a rice table works. Now, there are a lot of different things that you can do with a rice table. You won't always be given the value that you have at equilibrium. So sometimes it'll give you just initial concentrations and you can solve from there. But sometimes you're going to start off with both reactants and products. So before you can use a rice table, you actually have to figure out what direction the reaction is going to proceed. Is it going to make more products, or is it going to reverse directions and make more reactants? Well, the only way to do that is to use our questionable Q. You've got to calculate Q to determine what direction the reaction will proceed. So let's take a look at an example problem. Now, the very first step here, so notice they're giving you moles of nitrogen monoxide, they're giving you moles of nitrogen gas, and moles of O2. and they're reaching equilibrium. So you have a combination of reactants and products. But note, they did give you the equilibrium constant value. Otherwise, calculating Q wouldn't do you any good. So we need to first calculate Q. Now recall, writing and calculating Q looks exactly like writing and calculating K, you just might not be at equilibrium. Now of course, if you're going to do that, so let's go ahead and first write our expression for Q. Just like K, this is a ratio of the products to the reactants. Or should I say a ratio of the concentration of the products to the concentration of reactants. I emphasize concentration because did you notice? They gave you moles. Oh, those dastardly people. Now, if they were nice, they would have just taken your moles and put them in a 1 liter flask and you'd win. We did not win in this problem. We have to take our moles and calculate molarity before we can plug back into this expression. So let's go ahead and do that first. Luckily, concentration's easy, just moles divided by liters. So when you take the given number of moles of nitrogen monoxide and divide it by the 1.5 liter container, you get a 1.5 molar concentration. You need to go ahead and do the same exact thing for N2 and O2. Luckily, these also give you very pretty concentrations. So the 0.0749 moles in 1.5 liters is 0.05 molar, which is actually the exact same concentration as the oxygen gas, because that was just 0.0750, so a very tiny difference. Okay, now we have all the relevant values we need, so we need to go ahead and plug these values back into our Q expression and solve. So you should totally try that for yourself because it's so much fun, delicious math. And then go ahead and predict what direction the reaction will shift. When you're ready to check your answer, unpause the video. Okay, when we solve for Q, we got a pretty tiny number, but did you notice that K is also a tiny number, and in fact, K is tinier. Hopefully you remembered the trick to write these in alphabetical order. Since we wrote K before Q, it is going to be pointing in the direction the reaction will be shifting. This time, this reaction is not going to be proceeding in the forward direction from these conditions. It's going to be proceeding in the reverse direction. It's going to shift left. Well, this is going to make our rice table all sorts of interesting. First, let's go ahead and fill in. We know the reaction, and we know the initial concentrations. So let's take a moment, fill those in, and then when you're ready to check your answers, unpause the video. Okay, so these are initial concentrations. Now the fun part. Remember how we determined that under these conditions we're going to actually make more reactants? That means you're going to lose products. So instead of being a plus X like we normally would on the product side, whoops, I almost wrote it anyway, you will need a negative X because some of these products are going to be converting and forming reactants. So that means on the reactant side, now we're actually gaining a positive 2X. Which you might think is kind of crazy, right? We've already got so much NO. What are we going to make more of it for? Well, that's the way equilibrium works. It has a really tiny equilibrium constant, so this reaction is extraordinarily reactant favored. So under these conditions, we just need more reactants. So let's go ahead and fill in the very last column, or the very last row. When you're ready to check, unpause the video. All right, we've filled in our beautiful rice table. But you may be wondering, wait a second, I don't know what X is. How the heck am I supposed to figure out what these equilibrium concentrations actually are? Well, you may not have X, but you have the equilibrium constant. So we can just set up the equilibrium constant expression and then do some tasty algebra and solve for X. Let's try it. First, of course, we just need to write the equilibrium constant expression K. And then we can plug in our values from the equilibrium row of our rice table. Did you notice that because N2 and O2 have the exact same expression for their equilibrium concentration, we can actually just write that as being squared? And now, since we know what K is equal to, we can set that equal to that number. Now, the fact that both of these are squared makes our lives so much easier, because if it wasn't that way, we'd have to use a quadratic equation, and that can be kind of annoying, but instead, we can solve by just taking the square root of both sides. So that's a super messy way to show that, but that's exactly what we're going to do. So now, once we've taken the square root of both sides, mathematically, we have a new expression to solve for X. Now we just need to solve for X. And this is one of the many reasons why algebra is a prerequisite for this course. So I strongly recommend at this point in time you pause the video and you try this. Figure out what x is equal to. It's beautiful. When you're ready to check, unpause the video. So first we multiply both sides by 1.5 plus 2x to get it out of the denominator. And then we can distribute the 1 times 10 to the negative third to both of the things in parentheses. Next we need to combine like terms, so the terms with the x's together and the terms without the x's together. And then finally divide to solve for x. Yum, algebra! So you may be thinking, woo, I'm finally done. Not yet. Almost. Because that's just your x value. Now you need to plug x back into your equilibrium expressions and find the actual equilibrium concentrations. But that's short and sweet. So once we plug in the values for x, we'll have our final concentrations. And now you finally have your equilibrium concentrations, which was the whole goal of the whole problem. So yes, problems like this can take a little while, and that's okay. They're usually worth a lot of points on a free response. Conveniently enough, if you have the time, you can also check your work and make sure that you did it right, because you can take these concentrations that you solved for and plug them back into your equilibrium constant expression. Remember, our equilibrium constant expression said that K was the concentration of nitrogen gas times the concentration of oxygen gas divided by the nitrogen monoxide concentration squared. So let's plug in these values. So when I plug those in, gloriously enough, I get 1 times 10 to the negative 6th. Which is good, because that is exactly what my equilibrium constant was equal to. So that is a really good sign. It will not always be quite that perfect. Sometimes with the inevitable rounding, it will be a little bit off, but it should be close enough. There you have it. That is the basics of rice. So you are now ready for your next fun and exciting video, all about the different approximations you can use to make solving these pesky rice tables more delicious and slightly less long. So I'll see you there.